one is the current which is flowing on the secondary. So the secondary current, when there is an increase in load on the secondary side, when there is some increase in load on the secondary side, then the secondary side current will increase. That will make a demagnetization effect on the secondary side. So there is some mutual flux. Already there is some mutual flux because of the current flowing on the secondary. There is going to be an there is going to be a flux which is established by the secondary current which is flowing in the circuit. So that flux will be like this. Then that flux will be opposing the mutual flux. So that flux will be opposing the mutual flux. Because of that, the mutual flux will reduce momentarily. So if the mutual flux reduces, then the induced EMF on the primary side will reduce. If the induced EMF on the primary side will reduce, then more current will be flowing through that. That we have seen. So the current I1 will be increasing. Then there is some shunt component. Then when the load is increasing, then the balancing current will be increasing. Now this balancing current is increasing. So means that this is primary MMF. The primary MMF will be neutralizing or compensating because of the demagnetization effect which is happening because of the secondary MMF. Okay, so means that when the current is increasing on the secondary side, the MMF is N2 into I2. That will be opposite to the mutual flux. So since it is opposite to the mutual flux, it will reduce the overall effect of the mutual flux. Because of that, the primary MMF, that is given by IB into N1. This is for the balancing part. So this is the balancing part which is going to neutralize the secondary MMF. So the balancing minus the demagnetizing part will be equal to the 0. So if you add balancing and demagnetizing part, both will be equal to 0. I mean, subtraction of that will be equal to 0. Then from this circuit diagram, you can understand that I1 is the current which is coming out of the source, and balancing current is the current which is compensating for the demagnetization effect because of the load current. IM is the magnetization current. So this is the output current of the source, balancing current, and this is the magnetization current. And there is one current which is flowing through this path, that is I2, that is given by the load current. Now the overall magnetization effect. So this, if you are neglecting this losses, this loss is very less generally. This loss is very less. So we are neglecting this loss. So other than that, the MMF created by the primary, complete primary, minus the MMF on the secondary will be equal to the MMF divided MMF created by the magnetization part. Okay, so the MMF created by the magnetization part, you can consider like this: N1 into I1. This is the primary side plus sorry. So this will be equal to N1 IM plus N2 I2. So this is the total MMF part which we are going to get. Now, when this primary MMF minus this secondary MMF will always be equal to the MMF created by this part. Okay, the MMF created by this part is given by subtraction of this primary MMF and secondary MMF. Okay, so now if you rewrite this expression, if you are just dividing it by N1 throughout this equation, we will be getting this two will be cancelled and this two will be cancelled. Already we saw N2 by N1 is some ratio. Okay, so now this N2 by N1 into I2, N2 by N1 into I2, you can call it as IB. Okay, so how this is coming is, here you are having N2 turns and here you are having N1 turns. So the increase in current on the secondary side is related to this balancing current. So I told that IB will be proportional to I2, or you can also say that it is in the reverse way. So I2 is you can say it in the reverse way. I2 is proportional to IB divided by IB. So now there is only one thing, that is the ratio. So if you equate the MMF on both the sides, so IB into N1 will be equal to I2 into N2. So if you rewrite this expression, we will be getting IB is equal to N2 by N1 into I2. So that is what we have written it here. So now this overall term can be written as IB, or you can also write it as I2 dash, or this you can write it as balancing current or I2 dash. So now this part will be equal to Im. So this is the magnetizing current. So this is the summation of this. I1 is equal to IB plus Im. So that also you can say this is the equation which you have obtained from this. Now based on this, we can draw the overall diagram and we will be making the equivalent circuit from this. Okay, now there are three fluxes. You can see very clearly phi 1 is there, that is because of the primary current. Then the mutual flux is there, that is because of the magnetization current, and I2 is the flux which is established by the current which is flowing on the secondary terminal. Three fluxes are there. So phi 1 is there, phi m is there, then phi 2 is there. So when the phi 2 is increasing, that will be in the demagnetization effect, and phi 1 will be supporting phi m, phi 2 will be opposing. These two will be opposing, these two will be opposing, and these two will be supporting. Okay, so when phi 2 is increasing, then this phi m is going to decrease. If the phi m is going to decrease, then proportionately this phi 1 is going to increase. This is the load during the load time. This is only happening. Phi 2 is increasing, so the phi 2 is opposite to phi m. So when this is opposite to phi m, the mutual flux is reducing. If the mutual flux is reducing, then phi 1 need to increase, because here you can say that when phi 1 is decreasing, then induced EMF on the primary side is decreasing. When the induced EMF on the primary side is decreasing, then the current flow on the circuit, that is I1, is going to increase, because I1 is given by V source voltage minus induced EMF divided by Z. Okay, so this is what is going to happen. Then I1 is going to increase. When I1 is going to increase, then that is going to increase the phi 1. When phi 1 is increasing, already I told that the phi 1 is going to support this phi m. So because of that, the mutual flux is going to increase. Now the current is increased. Okay, so that is the thing which is happening in this transformer when the load is increasing. Okay, now we will be seeing about the equivalent circuit. Now, when you are talking about the equivalent circuit, so already we have seen why we need this resistor and why we need this inductor. So now you can see here that I did not draw the leakage flux. That leakage flux is represented by this inductor. Similarly, the leakage flux on the secondary side, that is also represented by this inductor. Now, this is the initial circuit. This initial circuit, we are going to make a circuit like this. Okay, the initial complete transformer is going to be represented like this. That is what we are going to do. So how we are going to do that, we will be seeing. This is the complete equivalent circuit. This is the approximate equivalent circuit. You can see here that this is the approximate equivalent circuit. From the actual circuit, we are going to bring it to this circuit. So we are going to see how we are going to obtain this final circuit. Okay, so this is the actual circuit. In this actual circuit, now we are having this copper loss on the primary side, and this is for the leakage flux on the primary side. This is the copper loss on the primary side and the leakage flux on the secondary side. Now if you apply KVL to this equation, so you can write V1 is equal to I1 into R1 plus J into X1 plus I1 plus E1. So this you can write based on this primary side. On the secondary side, you can write it as E2 is equal to, if you are writing KVL to this equation, E2 is equal to V2, that is the load, plus I2 into R2, that is this voltage drop. Then the voltage across this inductor is J into X2 into I2. Okay, so this is the thing. From this, we are going to represent this complete magnetic core as like this. Means you are having what are all things you are having here? You are having N1 turns, and here you are having N2 turns. This is on the primary side and this is on the secondary side. Other than that, there is one magnetic coupling which is made of iron. So this magnetic coupling that is made of iron, we are going to represent it as a two double slash line. This is going to tell that uh, it is coupled with iron material or magnetic material. Okay, that's why when you are using auto transformer, you will be using some structure like this, where this double line tells that there is some iron material which is linking both primary and secondary. Okay, if there is no iron material, if you are having just two coils like this on the just you are having two coils like this on the primary and secondary without any magnetic material, then you can remove this double line when you are drawing the equivalent circuit. But as of this circuit is concerned, you are having the magnetic core which is linking primary and secondary, so we have represented with two slash lines, which is going to represent the magnetic core and which is of iron in material. Now, when this material is represented like double slash, then what are the other things you are having? You are having n1 number of turns on the primary side and n2 number of turns on the secondary side. That is represented with the number of turns on this primary side and secondary side. Okay, so here two dot symbols are given. So here the dot symbols are given in such a way that the EMF induced direction is like this. You can consider like this. So wherever you are having this dot terminal, as of now you consider that you are having the positive polarity. You are having the positive polarity wherever you are having this dot symbol. So here in this positive polarity, current is going to enter. Here in this positive polarity, the current is going to leave the secondary terminal. Okay, now we have included the copper loss and we have to include the core loss. Okay, already we have discussed about what is core loss and what is the magnetic flux linking primary and secondary. So that we are going to implement here. Now, this is the actual circuit which we had in the previous page. So I1 is the primary current which is coming out of the source. I2 is the current which is flowing into the load. Okay, now we want to represent the core loss and we want to represent the magnetic flux which is linking primary and secondary. Okay, so that magnetic flux which is linking the primary and secondary is provided by the magnetization current. So that magnetization current should be coming from the primary side. So we are drawing the magnetization current on the primary side, and this resistor is going to represent the core loss, and this inductor is going to represent the magnetization part, which is going to be responsible for the mutual flux. Okay, now just a minute. This is going to be responsible for the mutual flux. Now you are having some current which is coming out of the source. That current is going to be divided into two parts. One is the balancing current and another one is the magnetization current. This magnetization current is going to further split into two things. One is the current flowing through this resistor and the other is current flowing through this inductor. The current flowing through the resistor is responsible for the core loss in the system, because in the transformer. So the core loss is represented in the resistor because there is going to be a heat dissipation because of the eddy current loss which is going to happen in the system. Other than that, there is some hysteresis loss. So because of that also, we can say that the overall loss is represented, the overall core loss is represented as a resistor here. Then there is one thing, that is a mutual flux. That mutual flux is going to link the primary and secondary. Okay, so why this is in parallel is the E1 which is flow V1, that is the source EMF, that will be 90-degree leading the current which is flowing through this, exactly 90-degree leading to the current which is flowing through this, provided if you are neglecting this elements. If you are neglecting this element, then the voltage across this shunt component is V1. So at that time the current flowing through this will be 90-degree lagging this voltage. So this is the current which is going to be exactly 90-degree lagging to this lagging to this voltage E1. Okay, then there is one component which is in phase with this voltage, that is going to be responsible for the core loss. Now what we have done, we have included mutual flux, we have included the mutual flux, and we have also included the losses because of the mutual flux, which is linking both primary and secondary. In the primary and secondary, the linking part is the magnetic core. So in this magnetic core, you are having the mutual flux. Because of the mutual flux, there is some loss in the core material. That loss is represented by the resistor, and the flux which is represented, which is linking both primary and secondary, that is a mutual flux, that is represented as the inductor here. So now we are having only a simple turns N1 and N2. The EMF induced on the N1 is E1 is the EMF induced on the primary side. E2 is the EMF that is induced on the secondary side. Now we want to remove this element. Okay, we want to remove this element that is given by the number of turns and the ion material. Okay, so now if you want to relate this in the single equivalent circuit, you want to remove this component. How you can remove this component? Okay, so you can see here that if you want to remove this component, the voltage across this point, across this, and voltage across this need to be same. But you can see here that the EMF induced on the primary side, it's not equal to EMF induced on the secondary side, because when N1 is greater than N2, or N1 is smaller than N2, the EMF on the primary side and the EMF on the secondary side, it's not going to be same. It's not going to be same. So what we are doing, we are going to change this N2 number of turns or N1 number of turns, which will make E2 as same as E1. Okay, so now, as of now, the N1 is not same as N2. Because of that, what is happening, the EMF induced on the primary side is not equal to the EMF induced on the secondary side. When these are not equal, you cannot merge this part. Why we want to make this equal? So if you are having two different terminals like this, when you want to merge these two things, then if you say that the EMF induced here and the EMF induced here are same, so in order to remove that joining part, you can merge these 2 points if both the EMF are same. When both the EMF are same, you can merge these 2 points directly. So in order to make these two values as same, what you are doing, you are going to change the number of turns on the secondary side or number of turns on the primary side in such a way that you make E1 is equal to E2. Now in this case, I'm making N2 as equivalent to N1. N2 I have some value, I wanted to make as equivalent to N1. That is what I am doing here. Whether my screen is visible to you?
Yes, sir.
Okay, fine. Thank you. Already we have seen one thing, that E1 divided by E2 is equal to N1 divided by N2 is equal to A. Okay, so the E1 can be made equivalent to E2 by multiplying with A. Okay, so if you just take this part, if you are just taking this part, you will be getting E1 by E2 is equal to A. So now E1, in order to make E1 is equal to E2, I need to multiply this A with E2. Okay, this A into E2 is called as E2 dash. So similarly, if I relate this N1 by N2 is equal to A, then I want to change this N2 in such a way that which is made equivalent to N1. So N1 is equal to A into N2. This is N2 dash. Now the N2 is changed to N2 dash. If I make N2 is equivalent to N2 dash, then the N1 will be equal to N2 dash. Then when both the number of turns are same in the primary and secondary, the induced EMF on the primary side and secondary side will be equal. So once I make N1 is equal to N2 dash, the number of turns on the primary side and the number of turns on the secondary side will change. Means will be equal to same. N E1 is equal to E2 dash. So you can also say that N1 uh, N1 is equal to N2 dash. So when these two are made equal, the EMF induced across this term will be same equal. When N1 is equal to N2 dash, then EMF induced on the secondary side will be equal to the EMF induced on the primary side. So when you have changed the EMF on the secondary side, here you are having some EMF. Let's say that some EMF is induced. Because of that EMF, some current is going to flow in this path. Now what we have done, we have changed this E2, which is made equivalent to the E1. So the voltage magnitude of this E2 will be changed. That changed value will be given by A into E2 bar, E2 bar, that is the phasor value, that is nothing but E2 dash. Now the voltage magnitude is changed. If the voltage magnitude is changed, then the current flowing through this path will be changed. So since the current flowing through that path is changed, the voltage drop across each element will be changed. Now what we are doing, once we are varying this, or once we are making this voltage equivalent to the primary side, all the other parameters which is available on the secondary, that also should be made equivalent to the primary. So now here you are having R2 dash, that here you are having R2 before conversion. After conversion you are making R2 dash, whereas R2 dash is equal to A square into R2, that we will be seeing why A square term is coming. Then this inductor term can be represented as J into A square into X2, that is nothing but J X2 dash. Okay, here you are having R2, here you are having R2 dash, here you are having JX2, here you are having JX2 dash, where R2 dash is given by A square into R2 and X2 dash is given by A square into X2. So that is the only things which are changed in the resistor and inductor. Then the load voltage, that also need to be changed. The load voltage is given by V2 dash is equal to A into V2 bar. So why we are changing it? So the concept behind that is the voltage and current relation before and after the voltage and current relation on the secondary side should be same even after we made primary voltage as equivalent to the secondary voltage. So if you see the secondary voltage, the relation between the secondary voltage and the secondary current should be same even after you convert, or even after you made secondary voltage as equivalent to the primary voltage. So means that the voltage and current relation on the secondary side never changes. Okay, so in order to make, or in order to maintain the voltage and current relation on the secondary side, we are make this voltage and inductance, voltage across the resistor and voltage across the inductor also, we are going to make it equivalent. So in order to make it equivalent, we have to change this resistor value and we have to change this inductor value, that is given by this relation. Similarly, we have to change the voltage across the load also. The voltage across the load was given by V2, that also we are changing it to V2 dash. Okay, now after you make this two as same, once you make the voltage that is on the primary and secondary as same, that is E1 and E2 dash, now the EMF across these terminals and the EMF across this terminal both are same. That is AB, the voltage across VAB will be equal to voltage across VCD. Let's consider this is C, this is D, and already we have changed the current flowing through this circuit. Now this is the current which is going to be flow here, that is I2 dash. Okay, now we can merge this part, by removing it. Actually what they will do, they will just move this. Okay, you don't consider like that, you just think that we have made the EMF equal to 0 on the primary side and secondary side, and so we are removing this part. So once you remove this part, what we will be having, this part you remove, then after that you will be getting the complete circuit like this. Now you can see the circuit is changed like this. The EMF across this is nothing but E1, or you can also say that E2 dash, or you can also say that A into E2. Then once you remove this, and if you are connecting this, then you are removing this and connecting these two terminals, then the current flowing through this part is going to be coming from here to there. So now you can see that IB and the current which is flowing here, that is I2 dash, both are equal. Already we have seen in the previous thing, IB is equal to I2 dash in the previous slides that we have seen. N2 divided by N1 into I2. So this we wrote it as I2 dash. Now the same relation we have got it here, I2 dash, the same relation we have got it here. So the balancing current is going to flow through this, that is same as the current as I2 dash, that is going to flow in the load. Okay, now this is the complete equivalent circuit of the transformer. Okay, so now you are having a two series inductor and capacitor. So this is for the primary side copper loss, this is for the secondary side copper loss, this is for the core loss, and this is for the mutual flux which is linking primary and secondary. So this is the complete equivalent circuit which we have obtained from the actual transformer. Now we will be just seeing about in open circuit test and short circuit test what we have done and what are the things we are obtaining from the open circuit test and short circuit test. From the open circuit test, if you just made this equivalent circuit like this, I'm just saying it without drawing the actual circuit. So in open circuit test, what you are doing is you are going to find the parameters in open circuit. In open circuit test, what you are doing, you are finding the shunt parameters. This RC and XC you are obtaining in open circuit test. In open circuit test, the secondary is going to be open circuited. If secondary is going to be open circuited, this is the equivalent circuit of the transformer. When the secondary is going to be open circuited, from this equivalent circuit, you can understand that whatever is the current flowing through this part, that is going to be IM. It is a series path. Here the current flow through this path will be equal to 0. So in the open circuit test, whatever the current which is going to flow through this path, that is going to be related only to compensate the core loss. So in open circuit test, you are going to obtain the core loss because in open circuit test, the current drawn by the transformer will be very much lesser when compared to the rated current. When the rated current is very much, when compared to the rated current, the current flowing through this path is very less. So because of that, the voltage drop across this particular element or the loss across this particular element will be very much lesser. Those who have performed the experiment in the lab, they could have seen that the actual transformer rating is 13.6 ampere. The current drawn during the open circuit test may be around 2 to 4 ampere. So this 4 ampere will be comparatively lesser than this. Because of this, the voltage drop across this resistor, across this series element, similarly the power loss across this element, it will be very small. So it is considered that whatever the current drawn, that is going to flow through the shunt element, and whatever the power measurement shown by the wattmeter, that is the power loss is happening in the core. So that is what you are measuring in the open circuit test. You are measuring the core loss of the transformer. So once you are obtaining the core loss and once you are obtaining the current, you already know the source voltage. Once you know the source voltage, and we are neglecting this part because the voltage drop across this element is very less. Once you obtain this Vs and once you obtain this Im, so if you are giving the rated voltage, that is 230, then you know Im by measurement. Similarly, you know the power loss that is happening in the system. Now with this, you can obtain the value of RC and you can obtain the value of XC. So it is just that you know IM and you know RC, you need to find RC and you need to find XC, right? So just by relating these two, current and voltage, so here you will be getting V divided by I you will be getting some impedance, that is Z. Okay, V divided by Im will be giving some impedance, that is Z. Okay, so now this current Im is the current which is going to be split it into two things. One is the current flowing through the resistor, that is IC, and there is one more current that is flowing through the inductor, that is I5, let's say. Okay, so now you are having Z. You are having Z. Now the Z can be drawn from the right angle triangle. This is R, this is X, and this is Z. Okay, how I have drawn this? If you take a series RL circuit, if you take the series RL circuit, then if you just take a series RL circuit, or let's say you just take a series RL circuit, then you can understand. So here, let's say this is R, this is X, and this is source voltage. So the current flowing through this is I. So if you are drawing, if you are writing the voltage equation, then from that, if you are drawing the phasor diagram, you can say that Vs is equal to I into R plus I into X, the into J. So now, if you draw the phasor diagram for this, you can draw I into R, which is like this. So this is I. Let's consider that I is the reference. Then the voltage across the resistor will be in phase with that. So this is nothing but IR. Then the voltage across the inductor will be 90-degree leading with respect to the voltage, with respect to the current. This is 90-degree ahead of the current. So that's why we are having J term here. Then the summation will be Vs. Okay, now this Vs can be written as I into Z. I into Z. Now, if you cancel I throughout this equation, then you will be getting Z here. You will be getting X here. We are getting R here. Okay, because I into R, I into Z, and this is I into X. So you are canceling I throughout this equation. Then you will be getting this right angle triangle, that is R, X, and Z. Now, if you have some angle theta, now Z is the hypotenuse and X is the adjacent, and R will be the, sorry, X will be the opposite and R will be the adjacent. So you can write cos theta is equal to adjacent divided by hypotenuse. You will be getting R divided by Z. So similarly, if you write it in sin theta is opposite divided by Z, that is the hypotenuse. You will be getting X divided by Z. So now you can find Z, R is equal to Z into cos theta. How you know the Z? Z can be obtained from this expression. You know the voltage equation, voltage value. Similarly, you know the current which is flowing through that magnetization part. If you are taking the ratio in AC circuit, V by I ratio is giving Z. Once you know the Z, you can find R divided by Z will be equal to cos theta. Then you can find the value. Okay, so now we need to find this cos theta. We need to find this cos theta, that again you can obtain from the core loss. You are measuring the core loss. From the core loss, we can obtain this cos theta. Then you can substitute that cos theta in this equation. Then you can find the value of R. So this is the parallel shunt element which you are going to obtain in the open circuit test. Okay, so in open circuit test, what you are doing, you are open circuit the secondary terminal. Then after you open circuit the secondary terminal, you are going to find the shunt parameters. You are going to find the shunt parameters or core parameters. So here the core loss is given by this RC and the magnetization part is given by this XC. Okay, so here in open circuit test, you are going to apply rated voltage, that is 230 volt. Then after you apply the rated voltage, you are going to measure the current flowing through that circuit. Then we are assuming one thing, that the voltage drop across this and the power loss in this series element is negligible, because the current flowing through this path is comparatively smaller when with respect to the rated current. Because of that, you can consider that the voltage across this source will be equal to the voltage across this shunt element. Because of that, the current is flowing only through this path, because this path is open. So then from that current you can find the Z. Once you are finding the Z, you can find this R value and XC value, how you can find it. You are also obtaining the core loss. Once you are obtaining the core loss, you are getting some value, that is VA cos theta. So this is the value you are measuring from the watt meter. So from this you can obtain the cos theta. Once you are obtaining this cos theta, because you know the value of V and you know the value of I, because you are measuring the voltage and current separately in the open circuit test, then from this you can obtain the cos theta. Once you obtain the cos theta, you can substitute in this equation and you can find the value of R and Z using this relations, R and X using this relations. So this is why you are doing the open circuit test. Okay, so in short circuit test, what you are doing is you are going to do the same thing, but you are going to obtain the parameters. In open circuit test, you obtained the shunt element. In short circuit test, you are going to obtain the series element. Okay, so in open circuit test, you obtained this parameter, so that is given here. So now in the complete thing, you don't know this parameter and this parameter. Now in short circuit test, what you are doing, actually you are short circuiting the low voltage winding, that we will be seeing later. But what you are doing, you are short circuiting the one side of the transformer, then you are finding the series element. Okay, so here in short circuit test, once you are short circuiting it, you are going to obtain these values, that is the series parameters. Now there is going to be some current, that is Im. That current is need to be supplied from the source. Now in short circuit test, we are going to consider that this Im is negligible, because already the Im value will be very lesser. So if the Im value is very much lesser, that value is given for the rated voltage at V1. In short circuit test, what you will be doing is you will be gradually varying the input voltage in such a way that you will be getting the rated current on this side. Once you are doing that, what happens is this voltage will be very much lesser. Generally this voltage may be, sometimes it may be around 11 volt also. If 11 volt is there across the source, then the current Im will be very, 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 very small. If the current flowing through this shunt element is very, very, very small, then you can neglect this current. Okay, so the current, you are going to see it for the rated current, that is 13.6 ampere on the load terminal. So the load terminal only you are short circuiting it. So in the load terminal, you are bringing it to 13.6 ampere. So here the voltage across this shunt element is around 11 volt. If you see the voltage across this, if the resistance of this, it will be around more than 600 or 7,000, 600 or 700 ohm, or even more than that. So when the RC value is very much higher, then the current flowing through this part will be very much lesser. So 11 volt divided by 600 ohm, 600 ohm will be very much small. So similarly, this value will also be higher. So if these values are higher, the current flowing through this shunt element will be very much smaller. So when the current flowing through this parallel shunt element is very much smaller, then this complete part can be neglected. So once you are neglecting or ignoring this shunt element, the overall current you are considering that it is flowing about this path. So the current flowing through this path is around 13.6 ampere, that is the rated current. That current is higher, and this current flowing through the shunt part is very much lesser. So you can neglect this shunt element in the short circuit test. Then whatever the current flowing through this, that is going to be flowing only through the load. Now what we are finding in the short circuit test. In short circuit test, we are finding the series parameters which is given here. We are going to find the series parameter which is given here. And in short circuit test, you would have measured some power. So that measured power is going to give the power loss which is happening on the series element, that is nothing but the copper loss. That is going to give the copper loss value. And other than that, you are going to find the R1 JX1 R2 into JX2 in the short circuit test. So the open circuit test and short circuit test are done in order to obtain these parameters of the equivalent circuit of the transformer. So why we need to obtain this equivalent circuit of the transformer is with this equivalent circuit parameters, you can obtain the efficiency of the transformer. You can obtain the efficiency of the transformer at any loading condition without doing the load test directly. Okay, so the open circuit test and short circuit test together will be helpful to find the efficiency of the transformer, also the voltage regulation of the transformer at any loading condition without doing the load, without connecting the load directly. So in open circuit test and short circuit test, we are not connecting any load. Without connecting this load, what we are going to do, we are going to obtain the efficiency of the transformer. What is the efficiency of the transformer? The efficiency of the transformer is given by the output power divided by the input power. So now without applying the direct input power, we can obtain the efficiency of the transformer without conducting the load test. So the advantage is here, you don't need to have the load capacity in order to supply it from the source, but without connecting the load, we can directly find the efficiency of the transformer using this open circuit test and short circuit test. This we will be seeing it again, but before that, let us see what is E1. This we have already seen. So N1 by N2 is nothing but A, because this is given by E1 divided by E2. So this is nothing but A, that is the ratio of transformation. Okay, now we have already seen I2 divided by I1 is equal to A. I2 divided by I1 is equal to A. Similarly, E1 divided by E2 is equal to A. That is nothing but I1 divided by N1 divided by N2 is equal to A. Now, we have seen one equation that is given by A square into R2, and we have also seen one equation that is A square into X2. This is nothing but R2 dash, and this is nothing but X2 dash. So how we have got this, that only we need to see. Other than that, we have seen all the things. Okay, so this we have this I have discussed just now. So E1 is equal to RC into IC. So this is the EMF, this is the shunt element. In the shunt element, just now I discussed about this. If the voltage across this is E1, the voltage across this is E1, then the current flowing through this path, if you know the current flowing through the path, or if you know the resistance value, of course you can obtain the other parameter. So if you do not know the IC, if you know the RC, by doing the open circuit test, you will be finding the RC, and once you find the RC, you can find the core loss component, you can find the IC value. So IC value, from this you can write it as power loss divided by the current. Okay, so we have just we just have rewritten this equation, because P divided by I square, this P is the power loss component which you are measuring in the open circuit test, and I is the current which is flowing in that particular path, which will be helpful to find this components, R component, Z component, and this X component. Okay, similarly, the flux inductance can be given by E1 divided by I5. So in this parallel component, the current flowing through this I5, and here the the current flowing through this path is IC. Okay, so this we have already discussed, why we are doing this open circuit test and short circuit test. From open circuit test and short circuit test, we are going to find this. Okay, so what we did, we made E1 is equal to E1 in order to obtain a general equivalent circuit. So in order to make E1 is equal to E2, we changed the number of turns on the secondary, which is made equivalent to the primary, in such a way that we made E1 is equal to the primary induced EMF will be equal to the secondary induced EMF. Once you make primary induced EMF is equal to secondary induced EMF, that is going to make the change in the current in this path. So in order to keep the voltage and current relation on the secondary side as same, we changed the other parameters also, that is the inductor, inductor, resistor, and the load parameters on the secondary side, that also we made equivalent to the primary side. Okay, that is what we have done. So from this, we have obtained this equivalent circuit from the actual transformer. This relation we have seen. So this relation also we have seen already. Okay, now you can see for the copper loss, when the copper loss need to be same before and after changing it to E dash. When you are using E2, you had some copper loss. When you change it to E2 dash, then also the copper loss should be same when compared to the previous case. So what we are doing, we are making the this is before transformation, this is after transformation. So what we are doing before the transformation and after the transformation, the copper loss that is in this series element, when you had E2, you had some copper loss. Now after that you made E2 dash. Then after you made this to E2 dash, then the copper loss on the secondary side, that should be same as the copper loss on the previous transformation. Before the transformation you had some copper loss, that copper loss, and after the transformation the copper loss should be same. So you are relating those two. So once you are relating those two, the copper loss is given by I square r. So that is given here. This is after the transformation, you got I2 dash square r2 dash. So before the transformation you got I2 dash into r2. Okay, so if you are relating this, you will be getting R2 dash is equal to I2 divided by I1 dash, the whole square. That is nothing but, this is nothing but A. So you will be getting A square into R2. So I told that for the resistor
Sir,
component. Yes.
sir, we have class.
Okay, I will be completing this slide and you can leave. Okay, so here R2 dash is changed to R2 is converted to R2 dash. So this is converted by A square into R2. That is what we have done. That is based on equating the copper loss on the secondary side. Similarly, for the reactive term, if you are equating it, you will be getting x2 dash is equal to A square into x2. That is what you will be getting. Okay, so here the load kVA, that is the load power before and after the transformation should be same. So when you are equating that V2 dash into I2 dash, that is after the transformation, and this V2 into I2 is before the transformation, then if you are just rearranging this equation, you will be getting V2 dash is equal to I2 divided by I2 dash into V2. So this I2 divided by I2 dash is nothing but A. So this is going to relate the power. Then based on that, you get the transformation ratio A here. Now what we have done, we have just transferred the secondary terminals, which is equivalent to the primary terminals in terms of voltage and current. So when we make such kind, we can reduce the equivalent circuit in a proper way, and the complete set of transformer, this complete set of transformer can be represented as a equivalent circuit like this. Okay, how we have changed this R2 dash and X2 dash, that only we have discussed. Okay, so this transformation is considered as secondary referred to primary. So whatever the secondary parameters are there, that we have made equivalent to the primary. So you can consider this, that the equivalent circuit is made equivalent to the primary. So you can say that the secondary is referred to the primary terminals or primary parameters. Similarly, we did it from this end, to this end. Similarly, you can also do it in the this side also. That is called as primary to secondary. So the primary parameters can be changed equivalent to the secondary, that is called as primary referred to the secondary. Now we have changed from secondary to primary, so it is called as secondary referred to primary. Okay, so that's all from my side. If you have any doubt, you can ask, else you can leave the meeting. Okay, thank you for joining. That's all from my side. If you want to ask anything, you can ask, else you can leave
Thank
the
you,
meeting.
sir.
Thank you.
Thank you, sir.